Hello, welcome to the course SJPHY3BO3 Electrodynamics 1. The contents of this course is taken from Introduction to Electrodynamics by David J. Griffiths. In today's class, we will continue to discuss topics from Chapter 1, Vector Analysis. In the last class, we learned about vector addition, vector product, etc. Today's class, we will learn about some of the differential operations related to vectors. So I'm sure you all are familiar with ordinary differential operation. If you have a function f of argument x, then the derivative of f with respect to x is defined as df by dx. This is rate of change of function f with respect to x. Now, what is the physical meaning of the derivative? If you take a small change in the function as df and a small change in the argument as dx, then df is proportional to dx, and you can write df equal to df by dx into dx. Here, the derivative df by dx determines the proportionality. So it tells you how rapidly the function f of x varies when we change the argument x by a tiny amount dx. So if you plot f of x versus x, you can calculate df by dx at different points. So if you calculate df by dx here, you get a positive value. In this point, there is no change in function, so df by dx equal to 0. Here you get a negative value. So this is similar to the slope. You have positive slope here, zero slope here, negative slope here. So df by dx is also known as slope of the graph f of x versus x. Now let's scale up and see what happens if the function depends on multiple variables. So let's take a function t which depends on three variables x, y, z, and let's ask the question, how fast does t vary? Now in the previous case, it was easy to analyze because we have only one dimension. Now we have three dimensions, so you have to monitor the changes in x, y, and z direction. Using the partial derivative theorem, you can write an infinitesimal change in t dt as dou t by dou x into dx plus dou t by dou y into dy plus dou t by dou z into dz. So this gives you change in x direction, y direction, and z direction. Now this is a scalar product which I can write as dot product of two vectors. So dt equal to dou t by dou x x cap plus dou t by dou y y cap plus dou t by dou z z cap dot dx x cap plus dy y cap plus dz z cap. Now the second vector, this is the displacement. It gives you displacement in x, y, z direction. So I can call it as an infinitesimal displacement vector dl. And the first vector I call as del into t, which is known as gradient of t. So gradient of t is defined as dou t by dou x x cap plus dou t by dou y y cap plus dou t by dou z z cap. So gradient is a differential operator when the function depends on more than one argument. So first thing to remember is that gradient is always associated with a scalar. T is a scalar function here, and the output is a vector. So gradient is associated with a scalar and gives you a vector. Now what is the physical meaning of gradient? So dt equal to grad t dot dl, which you can write in the component form as the magnitude of grad t into magnitude of dl multiplied by cosine of the angle between these two. Now if you fix the displacement vector dl and if you vary the angle theta, and for what value of the angle you get maximum change in the function t. So cos theta can vary from -1 to +1. So maximum value of cos theta is +1, which happens for theta equal to 0. So when theta equal to 0, the displacement is along the direction of grad t, which means for a fixed distance magnitude of dl, dt is greatest when you move in the same direction as gradient of t. So gradient delta t points in the direction of maximum increase of the function t. So gradient gives you the direction of maximum change in a given function. Let's do a quick problem. Find the gradient of the position vector r equal to square root of x square plus y square plus z square. So this is a scalar. So by the definition of gradient, you can write grad r equal to dou r by dou x x cap plus dou r by dou y y cap plus dou r by dou z z cap. So we need to first do differentiation with respect to x. So this gives you 1 over 2 x square plus y square plus z square to the power minus 1 by 2, which you can write as 1 by square root of x square plus y square plus z square. Now you have to do differentiation of the inner term. This is the chain rule. So differentiation of y square and z square with respect to x gives you 0. So you have only 2x here. So this is the first component. Similarly, you have second and third component here for y and z direction. So 2 cancel and the denominator is common. So you can write x into x cap plus y into y cap plus z into z cap divided by square root of x square plus y square plus z square. Now the numerator is the position vector r and the denominator is the magnitude of the position vector. When you divide a vector with its magnitude, you get the unit vector in the same direction. So this gives you r cap. Now, if you go back to the definition of gradient, you can write this as a vector multiplied by the scalar function t. You can write gradient t equal to dou by dou x x cap plus dou by dou y y cap plus dou by dou z z cap multiplied by the scalar function t. Now this vector operator is known as del operator. So del operator is defined as dou by dou x x cap plus dou by dou y y cap plus dou by dou z z cap. So this gives you the differential function in 3 dimensions. Now remember, this is not a normal vector, this is a vector operator. So when you write gradient t, you don't say you are multiplying t with the del operator. You have to say del is a vector operator which acts upon the function t. Now there are 3 ways del operator can act. First one we have already seen, del operator acting on a scalar function which gives you gradient of the scalar function. Second one, it can act on a vector function and gives you a dot product. So if v is a vector function, you can take dot product of del operator and the vector function. This is known as divergence. Similarly, you can have a cross product which gives you curl. Let's first look into divergence. So from the definition of del operator, you can write divergence of v as del dot v, which is dou by dou x x cap plus dou by dou y y cap plus dou by dou z z cap dot the v vector in component form vx x cap plus vy y cap plus vz z cap. So this gives you dou vx by dou x, x cap dot x cap is unity. So dou vx by dou x plus dou vy by dou y plus dou vz by dou z. So remember, the del operator is always associated with a vector function and the output is a scalar. Now, what is the physical meaning of divergence? It is a measure of how much the vector v spreads out or divergence from a given reference point. So if you take in this picture the center point as the reference point, how much the function spreads out in different directions. So the length of this arrow corresponds to the strength of the function. You can see that the length is increasing, meaning the function is increasing in all directions. So at this point, if you calculate divergence, you get a positive divergence. So you can assume that this point is similar to a tip of a water tap. Now water flows out from the tip. So if you calculate divergence of the water flow at the tip, you get a positive value. On the other hand, if you imagine the center point as the hole in a sink, now water from the tap flows into the sink. So all the water is flowing into the center hole of the sink. So at this point, if you calculate the divergence, you get a negative value because entire function is converging into that point. If you calculate divergence for the second figure, you can see that the function is moving in one particular direction and the strength of the function at every point is same. The length of the arrow is same at every point, which means it is not spreading out, it is uniformly moving. So if you calculate divergence at any point here, you get a zero divergence. On the other hand, in the third case, you see that the strength of the function is increasing. So if you calculate the divergence at any point in this field, you get once again a positive divergence. Let's do a problem. Suppose the functions shown in the figure are, for the first case, VA equal to the position vector x into x cap plus y into y cap plus z into z cap. For the second case, the function is VB equal to z cap, and for figure C, the function is VC equal to z into z cap. Calculate their divergence. So you know the definition of divergence, it is del dot the function. So for the first case, you will get dou by dou x, x plus dou by dou y, y plus dou by dou z, z. This is 1 plus 1 plus 1, which is 3. So as we have discussed, for the first case, you get a positive divergence. In second case, we said divergence is 0. Let's see whether that is true. So del dot VB. VB has only z component, x and y components are 0. So you can write dou by dou x 0 plus dou by dou y 0 plus the third component. This is 1 z cap. So dou by dou z into 1. So first two derivative gives you 0. The third case, derivative of a constant is 0. So you get total divergence being 0. In the third case, once again, it has only z component. The divergence is dou by dou x 0 plus dou by dou y 0 plus the argument of z cap is z. So dou by dou z into z. So first two terms, the derivative is 0, third one will give you 1. So net divergence is once again positive. So this gives you how much a given function spreads out from the reference point. Now coming to the third operation, which is the cross product of a del operator and a given vector function. So using the determinant rule, you can expand the cross product as x cap, y cap, z cap, dou by dou x, dou by dou y, dou by dou z, vx, vy, vz. This is the definition of cross product of two vectors. Now you can expand this and write dou vz by dou y minus dou vy by dou z into x cap plus dou vx by dou z minus dou vz by dou x into y cap plus dou vy by dou x minus dou vx by dou y z cap. So remember, curl is always associated with a vector function and the output is also vector. So if you compare gradient, divergence and curl, gradient is associated with a scalar and it gives you a vector. The divergence is associated with a vector, it gives you a scalar, and curl is associated with a vector and it gives you a vector. And what's the physical meaning of curl? It is a measure of how much the vector v swirls around or curls around a given reference point. So if you look at this picture, the function is curling around the z-axis. So if you calculate the curl at this point, you get a non-zero value. And remember, this is a cross product, meaning the output is perpendicular to both these vectors. And particularly, the curl is perpendicular to the given function. So if the function is in the xy plane, curl will be along the z direction. In the second case also, you have the function moving along the right direction in the bottom half, along the left direction in the top half. So if you calculate the curl at this point, it's like a rotating effect. So once again, you get a non-zero curl here. Let's do this problem. Suppose the functions sketched in the figures are, for the first case, function va equal to minus yx cap plus xy cap, a function along the xy plane. And for the second direction, for the second case, function is moving only along one direction. So you can write function vb equal to xy cap. Calculate their curls. So to calculate curl, you need to write the components in the determinant form. And if you solve this, you get this is equal to 2z cap. So you have a non-zero curl along the z direction as we have predicted. In the second case, if you do this math, you get once again z cap, a non-zero curl along the z direction. So curl refers to a rotating effect of a given function about a given reference point. Now in the case of normal derivatives, we are familiar with product rules. There are 4 product rules. If you have two functions f of x and g of x, then d by dx of f plus g you can expand as df by dx plus dg by dx. If you multiply the function f of x with a constant k, then d by dx of kf, constant is unaffected by the differential. So you can take it outside the derivative and write k into df by dx. Similarly, product of two function f and g, d by dx of fg equal to f into dg by dx plus g into df by dx. Similarly, d by dx of f by g. Once again, you have to apply product rule. G into df by dx minus f into dg by dx divided by g square. So I'm sure you have learned this in your +1 +2 classes. So similar to the product rule of ordinary derivative, you can define product rules for gradient, divergence and curl. So for each operation you have 2 products rule. So total in 6 product rules are there. So first one, product rule for gradients. Gradient of f into g is, this is very similar to the product rule in the normal derivative, f into grad g plus g into grad f. Similarly, gradient of a dot b equal to a cross del cross b plus b cross del cross a plus a dot del into b plus b dot del into a. The product rules for divergence, del dot f into a, where f is a scalar, this is equal to f into del dot a plus a dot gradient of f. Similarly, del dot a cross b equal to b dot del cross a minus a dot del cross b. Product rules for curl. Curl of f into a, once again f is a scalar, f into curl of a minus a cross gradient of f. Del cross a cross b equal to b dot del into a minus a dot del into b plus a into del dot b minus b into del dot a. So I'll show you the proof for theorems 1, 3, 4 and 5, and proof for 2 and 6 you can do as a homework. Now before moving into the proof, there is an easy way to remember this. So always remember the thumb rule for any equation is LHS has to be equal to RHS, right? So when we say LHS equal to RHS, it should be equal in terms of magnitude, both should be equal in terms of unit, and finally both should be equal in terms of the nature. Nature means if on the left hand side you have scalar, right hand side should be scalar. If the left hand side is vector, right hand side should be vector. So let's take one particular equation, the third one, divergence of f into a. Now divergence always gives you a scalar. So LHS is a scalar, RHS has to be a scalar. That's the first thing we have to remember. Now you are taking dot product of a vector and a scalar multiplied by vector. So you will have two terms. In one term, the del operator will be associated with the vector. In the second term, del operator will be associated with the scalar. So first you get, since there is a dot product, this is del dot A. Now del dot A is a scalar. So the only option is you have to do a normal multiplication with the remaining scalar f. So this is your first term. Now second term, you have a vector here and a scalar here. You cannot write it as del dot f. This is meaningless, right? So the only way you can associate a del operator with a scalar is by writing a gradient. So this has to be gradient of f. Now gradient of f is a vector. Remember, left hand side is a scalar, so right hand side has to be a scalar. So this is a vector. The only way you can make it a scalar is by taking a dot product with the remaining vector a. So this is a dot gradient of f. So if you remember this thumb rule, you can write this equation without much problem. So let's see how to prove these theorems. Let's take the first one, gradient of f into g. Now you can expand this in terms of the del operator as dou by dou x f into g x cap plus dou by dou y f into g y cap plus dou by dou z f into g z cap. Now this is the normal product rule associated with ordinary derivative. So you can expand this. So first term becomes f into dou by dou x of g plus g into dou by dou x of f x cap plus f into dou g by dou y plus g into dou f by dou y y cap plus f into dou g by dou z plus g into dou f by dou z z cap. Now what you have to do is all the terms with common f we can pool together. So I have one term here, one term here, one term here. F is common, so I can write f into dou g by dou x x cap plus dou g by dou y y cap plus dou g by dou z z cap plus, in the remaining terms g is common, take it outside, g into dou f by dou x x cap plus dou f by dou y y cap plus dou f by dou z z cap. So this is equal to gradient of g and this is equal to gradient of f. So we can write f into gradient of g plus g into gradient of f. Hence the result. Coming to product rule 3, del dot f into a, where f is a scalar. So once again, you can expand the del operator and expand a in terms of its components ax, ay and az. You know how to do the dot product. You need to take the product of similar terms. We have product of x term, product of y terms, product of z terms. So this is equal to dou by dou x of f into ax plus dou by dou y of f into ay plus dou by dou z of f into az. So this is product rule of normal derivative. You can expand it like this, just like we have done in the previous case. Now look at the first terms in each of this. This is dou f by dou x into ax plus dou f by dou y into ay plus dou f by dou z into az, which can be written as gradient of f dot a, right? You get product of similar terms. Similarly, you can combine all the second terms, f into dou ax by dou x plus f into dou ay by dou y plus f into dou az by dou z, which is nothing but f into divergence of a. So divergence of f into a equal to gradient of f dot a plus f into divergence of a. Coming to the fourth product rule, divergence of a cross b. So you need to expand the del operator and also you need to find out a cross b. So a cross b you can write in the determinant form. In the first row you have x cap, y cap, z cap. Second row you have ax, ay, az. Third row you have bx, by, bz. So a cross b will give you ay, bz minus az, by into x cap plus az, bx minus ax, bz, y cap plus ax, by minus ay, bx, z cap. Now you need to take its dot product with the del operator. You get dou by dou x into ay, bz minus az, by plus dou by dou y into az, bx minus ax, bz plus dou by dou z into ax, by minus ay, bx. Now this is simply product rule. You need to apply product rule for the first term. You get these two. Product rule for the second term. You get these two terms. So keep repeating it. Just the same procedure we have done in the previous two cases. Now what you have to do is you have to combine similar terms. So you have one bx here, one bx here. Combine these two, you get bx into dou az by dou y minus dou ay by dou z plus you have one by here, one by here. Combine these two. Similarly, you have one bz here, another bz here. So you combine these two. Similarly, you need to find similar terms for ax. You have two terms with ax, two terms with ay, two terms with az, right? Now look at these terms in the bracket. So first let's take the first three terms. The terms in the brackets are nothing but curl of a. So this is the x component of curl of a, this is y component of curl of a, this is z component of curl of a. So first three terms are nothing but b dot curl of a. Similarly, take the last three terms. The terms inside the brackets are the x component of curl of b, y component of curl of b, z component of curl of b. So this is a dot curl of b. So divergence of a cross b equal to b dot curl of a minus a dot curl of b. So guys, this is just expanding the del operator in its component form, finding out various dot products and cross product and applying the product rule of normal derivative. You have to keep doing it in different permutation combination. You can find any differential operation for any of these vectors. Similarly, you can do for curl of f of a, just like the previous case. You just expand, apply the product, you get f into curl of a minus a cross gradient of f. You can do this as a homework. So I have given you proof for 1, 3, 4, 5. You need to find the proof for 2 and 6 on your own. So that's about differential operators. In the next class, we will discuss about double derivatives. See you. Bye.